Okay, can you hear me?
Yes, sir.
Okay, so uh, here's what we'll do today. The last, I think some of you have attended the TA sessions also, right? Is that correct? How many of you have attended the TA sessions here? Or how many of you do attend it quite regularly? Okay. All right. So what we'll do is, I think the TAs have done a good job in respect to discussing some of these questions, right, in the form of the solve with us session. So the TA recordings, session recordings have also been shared. So on Discourse, you'll be able to find the post containing the TA recordings. So what we'll do today is we won't discuss week 2 because not because week 2 is easy, but it's kind of not too hard in my opinion. And the TAs have already done a decent job. So what I will do today is we'll do a recap of linear algebra concepts that you have studied in Max 2, whatever is going to be relevant to MLF for the next 5 weeks. Okay, so roughly half the course is linear algebra. So it's like week 3 to week 7 is going to involve linear algebra concepts. And we won't, in week 3, what we'll do is we won't like revise all the content from Max 2. So what the prof, you will see what the prof does is he'll directly jump into matrix subspaces, row space, column space, and then he'll move on to this concept called eigenvalues and eigenvectors, and he'll just keep going on. So because he assumes that you have already done Max 2, which is true, but then it's also important to revise these concepts. What we have observed is historically students have kind of forgotten some of the concepts, or they've not brushed up those Max 2 concepts. So that's what we'll do today. I'll start with vectors and matrices. I have a set of slides that I used to present during Max 2 sessions. So I will use them. You can stop me if you don't understand anything. If you don't stop me, I'll assume that everything is clear and I'll keep going on. Okay.
Yes, sir.
Okay. So this is, just give me a second. What happened? Okay. It's visible, right? The slide.
Yes, sir.
Okay. Yeah. So we have, yeah. So we'll start with vectors and matrices. So what are vectors and matrices? Why do we study linear algebra in a course on machine learning? So the main reason is data. Okay. So data comes to us in the form of numbers, okay, which are neatly arranged in this case in a table. So what you're looking at here is a typical data set from, let's say, records maintained by a school. So this could be your CT data set, right? So your scores data set, for example, which you studied in CT. So you have uh, student as one column, mathematics marks, history marks as two other columns. So these are typically called attributes in a machine learning context, or features. So you have two attributes or two features describing each student. Okay. So these are going to be your features, and then you are going to extract some information from this data. So if you have no labels associated with this data, then you do unsupervised learning in the form of, let's say, density estimation or dimensionality reduction, all these things. If there is some label associated, so for example, you have a third column that says, so maybe this is mathematics and physics, right? And then you could try and see if you can predict, let's say, the chemistry marks, right? I don't know how much correlation there is between mathematics, physics, and chemistry, but assuming they are your typical PCM, you could try to do some predictive task, right? So in that case, it will become a supervised learning problem, right? So on and so forth. So data is typically represented as matrices and vectors, especially this form of data, which is called tabular data. Okay. So what is a vector? Vector is one of many things. So it's a set of ordered. So there's an ordered collection of items. It's a tuple. So you could call that a vector. in this case, the vector has a very clear meaning. It's describing each student. Okay, so this is vector describing student A, this is vector describing student B, and so on and so forth. Okay, and each of these things is going to be called the component of the vector. So 85 is the first component, 75 is the second component. Okay, they are ordered. So 75, 85 will be another vector, not the same as 85, 75. So all this you already know. So what is a matrix? Matrix is typically used to represent the entire data set, so to speak. So vectors represent individual data points. So each row here, you could think of it as a data point, and the data set is represented by the entire matrix. Okay. So we now dig deeper. So we have this notion called the column vector. Whenever we say columns of a matrix, you should immediately think of them as vectors. Okay, so the same 85 comma 75, this is the same vector. You could treat it as a row vector or a column vector. Okay, so in this case, this column will be treated as a vector. So each column of a matrix is a column vector. Likewise, you have the row vector. Okay, so this we already saw. So vector addition works component wise. This is already familiar to you. So if you have to add two vectors, you add them component wise. And how does scalar multiplication work? So it again works component wise. If you want to scale a vector by a scalar, you multiply each component of the vector by that corresponding scalar. Okay, so that is vector addition, scalar multiplication are two of the fundamental operations that you can do with vectors. Okay, so the next important concept is linear combination. So once you have vectors, once you know how to add vectors and scale them using scalars, you can combine these two operations, and that's what is called a linear combination. So 2 times some vector plus 3 times some other vector. Okay, so that will give you a linear combination. In general, if you have m vectors and m scalars corresponding to them, you could first scale. So remember that you're first scaling by the corresponding scalar and then accumulating these vectors, and the resulting this operation is called the linear combination. Okay, very important in linear algebra. So what are some of the so where do these vectors live, right? So what are some of the objects that we are usually used to associate with vectors? So the line is the first example. So you could technically you could look at each element of R, okay, the real line also as a vector, though we don't do it. We usually treat them as scalars, but you could in principle look at them as vectors. Okay, R2 is probably the closest example that we have of a collection of vectors, which we later on call a vector space. So R2 you are familiar with, is the plane, R3 is the space. And if you extend this, if you generalize this notion to n coordinates or n tuples as they are called, you get Rn. Okay, so Rn is the set of all points x1 to xn such that each xi is in R. Okay, so this is Rn. Our setting will be Rn for first 2 weeks, weeks 3 and 4, and then we will see that we move to Cn or complex. So complex numbers will come in when we enter week 5 in MLF. But for the first 2 weeks, it's enough if we understand how Rn works. Okay. So now we come to matrices. So remember that each matrix itself can belong to a space. So this is the space of all 3 cross 4 matrices, for example, M3 cross 4. So A is a 3 cross 4 matrix, is an example of a member in this space. Okay, so that's what I'm just written these things down. So it's M cross N would be the set of all M cross N real matrices. Okay, so when I say R, that means that each entry of a matrix from the set is going to be real. Okay, you could also have complex matrices. We will study complex matrices as I mentioned in week 5. Okay, so far any questions? These are all very simple concepts. Any questions? Not, I will proceed.
Sir, linear combination, sir, if you can just help me understand.
What is the question there?
What do you mean by linear combination?
Linear combination is just you just scale vectors and then add them together. You linearly combine them. So the operations scalar multiplication and vector addition, these together are called linear operations. So scaling and adding vectors together is a linear combination. So you're combining vectors, but you're combining them linearly, meaning you're adding them and scaling them, or scaling them first and then adding them. Okay. So yeah, so now we come to something that's very important. You have already seen this. I know some of you have seen this from 11th standard, 12th standard days, right? But we are taught this whole matrix multiplication slightly differently, but you must expand your understanding of matrix multiplication. So to that end, right, we'll first look at matrix vector product. Okay, how do you multiply a matrix and a vector? Okay, so how do you multiply generally? So you do 1, 3, 5, 3 minus 1, 2, right? So 1 into 3 plus 3 into minus 1 plus 5 into 2. That's your first element. And then you do the same for 2, 4, 6. That is your typical, that's how you view matrix products. But then that is not the only way to view the product of a matrix and another matrix, right? In this case, matrix vector. So the best way, in some sense, to understand matrix vector product is it's a linear combination of the columns, as you see here. So whenever you see a matrix vector product, this is of the form AX, right? A into X. What you should immediately go to is you are combining the columns of the matrix A using the elements in the vector X. Okay, so is this product clear to all of you? A into X, how it works?
Sir, could you explain the answer? Could you complete the answer once? Sir?
You can tell me, right? How will you complete the answer? What would you do next?
Is it 3, 6 and minus 3, minus 4, 10 and 12, and you add them?
Yeah, so you just multiply this, right? First you multiply, you get 3, 6, minus 3, minus 4, 10 and 12, and then you add the three vectors. So that will give you 10, what would it give you? 10, 2. Is that correct?
Yes, sir.
So this is 3 minus 3, 0, so 10. And then this is 6 minus 4, 2, or 14. I don't know. Some such thing, right? This is just vector addition finally. So, but the idea is clear, right, to everyone? This is linear combination of the columns. So you are
Sir, if the second matrix we are having a 3 by 2 matrix instead of 3 minus 1 2, if we are having a 3 by 2, then how would we multiply in this way?
I'll come to that. Okay, so that we'll come to matrix soon. I'll first cover matrix vector matrix, and then I'll go there.
Okay.
Okay, but it may seem as though I am like unnecessarily spending time on this, but this is a very important way of understanding products. Okay, if you don't understand this clearly, or rather, if you understand this clearly, several other things will become very simple. Okay, so when you see matrix vector, always think about it as a linear combination of columns. Okay, where the scalars come from the vector. Okay, 3 minus 1, 2. If you notice, those are your scalars, right? So 3 minus 1, 2 are coming from here, and the corresponding columns are coming from the matrix. Okay, so this is matrix vector product. So in general, if you have to generalize this, if you have a matrix having n columns, okay, you have C1 to Cn, and you have a vector which you are multiplying it with, and there are corresponding to the n columns, there are n coefficients, right? So if you multiply these two, what you'll get is that linear combination. So x1 times C1 plus x2 times C2, so on till xn times Cn. Okay, so what will be the shape of this matrix that you have here?
Is it square?
It need not be square. So if it is not square, what would it be?
Rectangle.
Rectangle, sir. Rectangle.
Correct, but yeah. So what will be the shape of that rectangle?
Number of rows will be less than number of columns always.
Is that necessary?
No.
Not necessary, right? So it could be anything.
Yeah.
So
N by N. M by
yes,
N.
correct. Some m by n, right? So m could be anything. So this is some m by n, and this is n cross 1, right? This is a column vector, and the result is also a vector, right? So you must keep that in mind. It's m cross 1. Is this clear? The shapes of the matrices and vectors.
Yes, sir.
Okay, right. So if you look at the spaces in which these objects reside, the matrix is in the space of m cross n matrices, and the vector is in Rn. This vector, the output is in Rm. Okay, so you must know to convert between the the relationship between the shapes and also the corresponding vector spaces where these are. Okay, so that is matrix vector product. So you could also multiply a vector first. You could have a vector first and then a matrix. So that will give you what is called a vector matrix product, right? So as long as the shapes match, you are fine. So this is like 1 cross 2 and 2 cross 1. Okay. So this is not that familiar to many people, but this is also a very important operation. If you put a vector in front of a matrix of the right size, then it turns out that this product is nothing but a linear combination of the rows. So this is like 3 times the first row minus 1 times the second row. Okay, so I just want you to keep this in mind. Matrix vector means linear combination of the columns. Vector matrix is a linear combination of the rows. Okay, therefore, if you generalize this, what you see, if you have m rows in your matrix, and if you want to multiply it by a vector before, that vector should have m entries, right? So then this just becomes x1 times the first row plus x2 times the second row plus xm times the last row. Okay, so I've used transpose because this is a row vector, right? So R1 is usually a column vector. So R1 transpose is a row vector. So in this case, R1 transpose is 135 and R2 transpose is 246. Is this clear? The vector matrix product?
Yes, sir.
Okay. So what are the
Yes, sir.
shapes? Yeah. So what are the shapes here? They are, this is in 1 cross.
1 is to, yeah.
Yeah, right. So what are the spaces? R M M cross n and Rn. Okay, so that is two products we have seen: matrix vector, vector matrix. Now we look at vector vector. Okay, this is something which is familiar to all of you. It's the dot product. So strictly speaking, you have the notion of inner product. Okay, but we will mostly work with dot product. We will see that when we come to week 5, once again, when we work with complex matrices, complex vectors, the dot product will not work. So you will have to go and look at a complex dot product. So therefore, that's why I've used the term inner product here to be safe. Okay. So remember
So
that.
is there any difference between these two, dot product and inner product?
Yeah, correct. Yeah. So good question. So this inner product is a more general idea. The dot product is a type of inner product. Okay. So there are different kinds of inner products which are possible. Dot product is one kind of inner product. Okay, so this is the dot product, right? So you just how do you compute this?
Sir,
Yeah,
sir, how will we identify those like they look alike very same like the inner and the dot?
how do we identify?
Like where to do vector vector multiplication and where to do vector and matrix multiplication?
That is from the shapes, right? It will become clear. For example, if you have a vector matrix, sorry, a matrix vector, then see, okay, one thing, I don't want you to confuse yourself with the different kinds of products. See, all of them are matrix products. Okay, there is no doubt about that. So you can still continue to multiply this like the way you do. Say 1 into 3 plus 3 into minus 1 plus 5 into minus 1. So sorry, 1 into 3 plus 3 into minus 1 plus 5 into 2. That is your first element. Second element, you can use the second row and this column. So you could still go back to that. All the
We'll
time,
get the same answer, right, sir?
yeah, you will get the same answer. But that is what I'm trying to impress upon you is that is not the only way of looking at matrix multiplication. That is actually a very limiting view. So if you stick to that, you will miss out on several ideas in the subject. Okay, so I want you to develop this facility to look at different kinds of ways of looking at the same operation. Okay, so if a vector comes to the right, you know to do linear combination of columns. Yeah, go on.
So the change in the vector spaces by multiplication Can you explain that with a graph maybe? Like it's going from 3D space to a 2D space by multiplication.
That is correct. So what will happen is you are collapsing the space onto either a plane or a line. So this is for this you'll have to understand, go back to linear transformations and all that. But even without going there, when you multiply, I'll just give you the words and then you can imagine, right? So if you multiply a matrix like this, right? What you are doing is you are collapsing the space, meaning, sorry, you are collapsing three-dimensional space onto either a two-dimensional plane or onto a line. So every point in the space is being mapped to either a point on a plane or a line. That's what is happening.
Okay. So
Okay, I hope
is there a difference between matrix multiplication and matrix and vector multiplication? I mean, is it the same way as we do matrix multiplication?
it is the same thing. Okay, it's just that I'm using, this is a vector, right? So it's a column vector or a row vector, right? So it's a matrix where one of the two dimensions is one.
Sir, no, sir. Sir, in this matrix multiplication, I have a little doubt. Sir, when if we do this by matrix multiplication, the resultant will be, I think, 1 into 3. The shape will be 1 into 3, right? 1 row and 3 column.
Correct. Yeah. Here also the shape is 1 into 3, right?
It is okay, sir. Thanks.
See, I'm not teaching you something new. Okay, so I'm not trying to erase your understanding of multiplying two matrices, right? All that I'm trying to do is add something to that knowledge. Okay, so that's all I'm doing. So you can, if it is more comfortable for you to multiply this as this way, okay, that's what you do, right? This
Yes,
way,
sir.
this way, this way, this way. That's correct.
Go by
That's, I'm not saying that's wrong, but then that doesn't bring out the essence of what is happening, right? What you're doing is something actually very meaningful. What you're doing is you're multiplying the first row by 3 and you're multiplying the second row by -1 and you're adding the two rows. Okay, so that's a much more meaningful thing to do than, you know, doing this, right? So this you know. So this is like a operation that you're so familiar with. Okay, going row column row column row column. So but also try to understand it this way.
Okay, sir.
Okay, so that is yeah, inner product dot product, that's where we were, right? So this is familiar to you, I hope. X1 y1 plus x2 y2, so on till xn yn. So that's your inner product. There is one more product, it's called the outer product. Okay, so this shapes are, one thing you have to notice here is that the dot product always returns a scalar,
Scalar value.
right? Okay, so you could call it a 1x1 matrix, but it's a scalar, right? So there is another important operation. It's called the outer product. It's actually a very interesting concept. It will come up in machine learning techniques. Some of you might have seen it. Those who have taken MLT and MLF together. So this would have come up in week 1. This will also make an appearance in probability and statistics when we do multivariate Gaussians, right? So meaning normal distributions which involve not just one variable but two or more variables. Okay, so the outer product is like this, right? So it's inner product. What did you do? You did row vector, column vector. In the outer product, what you're doing is you're doing column vector, row vector. Okay, so what are the shapes involved? This is 3 cross 1, 3 cross 1 and
1 cross 3.
1 cross 3. Therefore, you see that the output is 3 cross 3. So this is matrix multiplication only. We are not doing anything different, but it's called the outer product. Okay, so there's again a nice way of obtaining this. So notice the pattern here. You could obtain this matrix in two ways. Okay, you could either take, so first I'll do the one way, right? 1 2 3 you could take, you could fix 1 2 3. If you multiply 1 2 3 by 5, that's your first column. If you multiply 1 2 3 by 6, that's your second column. If you multiply 1 2 3 by 7, that's your third column. Do you see that that pattern?
Yes, sir.
Okay, alternatively, there's one more pattern. Can you see that other pattern?
Yeah, 1
Yes,
is
sir.
multiplied by 5, 6,
One
7,
more
2
time, please,
multiplied
sir.
by 5, 6, 7.
Right.
3 multiplied by 5, 6, 7.
Yeah, you could also look at this as multiplying the rows by these numbers, right? So this by 1 will give you the first row, this by 2 will give you the second row, and 5, 6, 7 if you multiply by 3 will give you the third row. Okay, this is not just we were not lucky. That's how it works. Okay, so if you generalize this to some m cross n matrix, okay, where you have m cross 1 and 1 cross n, same principle works. So you could either treat this as fixing the column and multiplying it by these values, or fixing the row and multiplying it by these values. Okay, so that's your outer product. So
Sir, if you can explain the way we are treating inner product and outer product, little bit confusing, sir.
they are two different things, right? So we are just calling it different things. So inner product, the output is always a scalar. Okay, the outer product, the output is a vector matrix. Okay, that's one difference. The other difference is that this is slightly more involved in the sense that it is tied with what is called an inner product space. You have studied inner product spaces in Max 2. If you remember, in week 6, 7, 8, somewhere around that point, you studied inner product spaces. So the dot product is associated with operations like getting the angle between two vectors, finding the distance of a vector from the origin, things like that. The outer product is not associated with any of those things. Okay. If you understand this distinction, for now it is enough.
Sir, one question.
Yeah.
This vector is always a single tuple?
Yes, you always treat it as a tuple of this form, some sequence of
Okay.
tuples. Okay, that is one way of treating the vector.
Okay.
Sir, any applications of this outer product? Because
Yeah.
I could see that inner product, will be used, to even to identify the orthogonality of the vectors.
Correct,
If
yeah.
I'm correct.
Correct, you are right.
But
So
similar kind of applications or usage of this outer product would be helpful, sir. If you could
yeah,
give us some insight, actually.
yeah, so the outer product you will see in this course itself and in the next course. So one use case is so if you notice, these are what are called rank 1 matrices. So if you remember rank, so the rank is the number of linearly independent columns, right? So there is only how many linearly independent columns are there here for this matrix?
I think only one.
Only one is there, right? So everything is a multiple of one column basically. So therefore these outer products are called rank 1 matrices, and they are very useful when it comes to decomposing a matrix into sum of rank 1 matrices. Okay, so this will come up in what is called singular value decomposition. When we study this in week 7, you will realize that you can express a matrix. So you can express a matrix, any matrix A, okay, of shape m cross n, okay, as sigma 1 u1, so v1 transpose, plus sigma 2 u2 v2 transpose, plus dot dot dot, plus sigma r ur vr transpose, right? So each one here is an outer product. Okay, so outer products are always of the form column vector into row vector, right? So this is so this outer products help in matrix decomposition. Okay, so matrix decomposition means splitting a matrix into different matrices, right? Simpler matrices that you can work with. So this comes up in later in week 6, week 7 as singular value decomposition. Okay, this is one place where it will come. The other place where it will come is calculating what is called the covariance matrix. Okay, you all know what the variance is, right? So variance is what? Sigma I equal to 1 to n. If you have an observation, if you have observations xi, then xi minus mu, minus mu whole square by
In
1 by n, right? So 1 by n equal to 1 to n. So this is the variance of a random variable, single scalar random variable, right? So what will happen for a vector random variable is the formula will look the same, but instead of xi minus mu, you will have xi minus mu into xi minus mu transpose. So this will be called the covariance matrix. Okay, so this is called the covariance matrix, and this is the outer product making an appearance there also. Okay, I hope for now that's okay.
Yep, sir. Thank you, sir, for giving
Okay.
heads up.
Yeah. So these are you have now studied 4 ways of multiplying matrices and vectors, right? Where so in each of these operations, at least one entry was a vector, right? So in this case, both are vectors in the outer product. In inner product also, both are vectors. In the vector matrix vector, one of them is a vector. Okay, so with this armed with this understanding, you can now start appreciating matrix multiplication. Okay, so there are for you to multiply two matrices m cross n, m cross p, the number of columns of A should be equal to the number of rows of B. So this all this you know. Okay, so only matrices of compatible dimension, all that you know. Okay, in general, you can't change the order of matrix product. So AB is not equal to BA. If the two are equal, we say that the two matrices commute. Okay, so if not, they don't. Okay, so in general, they don't commute. So you can't assume this for, you can't take this for granted. Okay, now we'll come to 4 ways of multiplying matrices based on whatever we have understood so far. Okay, the first is taking inspiration from matrix vector product. So if you want to multiply A and B, okay, so in all these cases, what you have to keep in mind is on the left, there will be two matrices. Okay, this is B. How have I represented B? As a set of columns, okay, as a set of column vectors. So there are P columns in B, right? So P is n cross P, remember. So I'm keeping A as it is, but capital B, I'm treating it as P columns. So you can think of matrix multiplication as A acting on each of these column vectors. Okay, so maybe we'll do a very quick example for the first case, right? So you have A as what is this? We could take 2 cross 2 for simplicity. So 1, 2, 3, 4. Okay, and B as say 1, 3, 2, 7. Okay, so some simple example. And you want to do AB. So AB, you know how to do it the usual way. But then what we'll do here is we will treat. Let's give this a color. So let's say this is red, and this is green. Okay. So how do you look at AB? You can split this into two operations, right? So you are A into 1, 2. Okay. And that is your first column, and A into 3, 7. That is your second column. So you can treat the product of A and B as this kind of matrix vector products. Okay, list of matrix vector products. So can you do this computation and let me know what you get? What will A into 1, 2 be? Okay, maybe I'll do it. Yeah, so based on what you have learned so far, what is A into 1, 2? How do you represent that?
1 times 1, 3. Sorry, 1, 3.
Okay.
Plus 2 times 2, 4.
Okay, so 2 times 2, 4. Okay. 2, 4. So this turns out to be 4 plus 1, 5, and 3 plus 8,
11.
11, right? So now multiply these two in the usual way, that the way you are used to doing. AB, if you look at the first column, what do you get? 1 into 1 plus 2 into 2, so that's 5, and 3 into 1 plus 4 into 2.
That one, 17.
Same thing. You get the same thing. It's just that you now view it differently. You look at it as A, you're fixing A, and then you're treating B as a set of columns, and then you're applying A to each column. Okay, so this is, I hope this is clear. This is clear, right? This example.
Yes, yes, sir.
Yeah. So that is matrix vector. Now, can you think of a different way of doing it based on what you have seen so far? If you had to do vector matrix, how would you do this? You can treat.
Sir, could you repeat your question?
So matrix vector you have seen. This is one way of multiplying two matrices where you keep A fixed and then treat B as a set of columns. I told you that there will be 4 ways of multiplying matrices, right? So what do you think could be the other way? If I call it vector matrix, how will I treat A and how will I represent B?
It's going to be B and A.
Okay.
Sir, the rows of A and will multiply with the elements from B.
Correct. Yeah, that's correct. So you treat B as fixed. Okay. So you treat B as a whole matrix, but then you treat A as a set of rows. Okay. So you treat A as a set of rows, and what happens is each row of the output is a linear combination of the rows of B. Okay. So here notice that each column of the output was a linear combination of the columns of A. Okay, A, B1 is a linear combination of the columns of A, right? So here A, B. So each row of the output is a linear combination of the rows of B. So if this is not clear, so you can go back to this example again. And what are we trying to do here? You are treating so I'm looking at the first row of the output. First row of the output will be this product. Okay. So what will this be? 1 into
1 into
1, 3, the first row, plus 2 into
2, sir.
okay. So what do you get? 4, 5.
5,
17.
5, 17, right? Now go back and multiply AB the way you are used to doing. So first row will be 1 into 1 plus 2 into 2, 5. So 1 into 3 plus 2 into 7. Okay, so that's same, you'll get the same thing. Okay, so I'm not suggesting that you start multiplying in this way. All that I'm saying is you can multiply this way also. Okay, so just know that this is possible. So you have seen 2 of them. The third is what you're used to. This is where the inner product comes in. So notice that the way that you are used to multiplying matrices actually involves the inner product. So you're taking, or the dot product. So you're taking the first row and you're multiplying with the first column, right? You're taking a dot product actually. So if you want the ith row jth element in the output, right? That is nothing but the dot product between the ith row vector and the jth column vector here. Is this clear to everyone? The usual method of matrix product. Okay.
Yes, sir.
Okay. Finally, you can also do outer products, which is what I just showed you, right? Matrix decomposition. This is a very, very useful way of looking at matrix multiplication, where what you're doing is you are treating. So remember that there are n columns here and n rows here. Okay, n columns and n rows. So you can actually break this down as a sum of outer product. So this example will probably help here. So let's go back. This is perhaps a very different way of multiplying matrices, but it's worth doing this fully. So let's first do AB using the usual method that we are used to. So far, what have we got? 5, 17, and what was the other one? 11?
37.
1137.
37. Okay, this is what we were used to. Now what we'll do is, what I'm claiming is this is actually 1, 3 into 1, 3. Unfortunately, both are 1, 3. That's fine. Plus 2, 4 into 2, 7. Okay. I'm claiming that AB is actually equal to this. So let's quickly verify that. So how do you multiply 1, 3 and 1, 3? You could keep the columns the same and then multiply it by the corresponding coefficient. So this will become 3 and 9 plus, what will this be? You could keep the rows same, for example, here 2, 7 into 2. So you have to multiply this by 2. So this will become 14, correct?
8,
And what will this be? 8 and 4 into 2, 7, right? So 8 and
28.
8, right? So if you now add them, so you get 5, 70, and 11 and
36.
right? So each of them is an outer product. So this is an outer product. This is also an outer product. Okay, and you have decomposed AB as the sum of two rank 1 matrices. Okay, so this is like you have decomposed AB as the sum of two rank 1 matrices as given below. Okay. All right. So we'll go back. So this is once you have understood this, right?
Sir?
Yeah.
Can you solve one of them? Like,
Which
sorry,
one?
can you go back to that slide?
Yeah.
Yeah, 1 into 1 into 1 into 3 and how I get 3 and 9, the lower row. AB equals to 1, 3, 3, 9.
Yeah.
That.
So if you want to multiply these two, the way to do that is first it will give you a 2 cross 2 matrix. Now, if you want, you can fix the column first. So for example, 1, 3 is the first column, right? And then you have to multiply it by the coefficients here. So 1, 3 into 1 will give you 1, 3. And then 1, 3 into 3 will give you 3, 9. You could look at it that way. Or you could also look at it as you keep the row fixed. So you multiply 1, 3 with 1. So that is 1, 3. And you multiply 1, 3 with 3. That is 3, 9. So you could look at it both ways.
So am I multiplying and adding?
No, you are not adding, right? You are only multiplying. You are just scaling each row by the coefficients here, or each column by the coefficients there.
Okay. Okay, sir.
Okay. So now if you combine all this together, or rather if you place them all together, these are the 4 ways of looking at matrix products. Okay. Once again, I'm not suggesting that you should follow anyone here. This you can stick to this because this is what you have been doing so far. But please note that the other ways are useful in their own right.
Decomposition one is useful.
Yeah. Right.
Sir,
That is
if you can just go to the previous slide, please.
Yeah.
Still, sir, the inner and outer, this thing is not clear, sir. What is the basic difference between these two?
It's just two different ways of doing the same thing, right? That is all.
Okay.
There's nothing more. I don't think there's anything deeper than that. It's just that each one will make an appearance in different application. So sometimes you'll have to do this. Sometimes you'll have to do this. Okay. So
Sir, are the rank 1 matrices useful?
useful in their own right? So yeah, everything is useful at some level, but the utility is going to be measured, right? So some things are extremely useful. The dot product, for example, inner product, is incredibly useful because it makes an appearance in several places, but you can't say that for everything, right? So it has its use, but you have to be careful.
Okay.
So the dot product, for instance, is useful in this area of machine learning called natural language processing, right? So where you represent words as vectors, words in text. For example, you have ChatGPT and all these things, right? So you can think of each word as being represented as a vector in some space, and the dot product will give you the information about similarity between words. So for example, words such as king and queen will have a higher dot product compared to say king and cricket. Okay, so king and cricket have nothing in common, so their dot product will be likely 0. But king and queen have a lot in common. King and ministers will have a lot in common. So this dot product is pretty useful when it comes to applications in ML, but you can't say the same of every concept in linear algebra. Okay, so that you have to keep in mind. Okay, so what are special matrices? You already know them. So you have the diagonal matrix. So where the non-off diagonal entries, right? So this is called the main diagonal. This is called the main diagonal. This is sometimes called the anti-diagonal, but usually we are only interested in the main diagonal. So the elements that are not on the main diagonal are 0. So everything here is 0. So what about the main diagonal? Can they be 0 for a diagonal matrix? What I'm asking is, consider a matrix like this. Let's say you have 1, 0, 1, 0, 0, 0, 0, 0, 0. Is this diagonal?
No.
No.
Yes.
Yes.
I think.
Why no? Those who said no, why do you think no is the answer?
So diagonal matrix, no diagonal elements, no should be a non-zero values.
Okay. So that is not needed actually. So a diagonal matrix by definition is one where the off diagonal entries, right? So when I say off diagonal, I mean the main diagonal, right? So main diagonal, I mean the one that goes from top left to bottom right, right? So that one. So the off diagonal entries are 0. That is all. That's the only requirement, right? So you don't mandate anything else. You don't say anything about the diagonal entries. They could be 0, they could be non-zero. You don't really bother about diagonal entries. The only thing that you care about is these guys should be 0 for sure.
And in this case, if these two ones also become 0, it is a complete 0 matrix.
Sorry, which one?
These two 1, these are also 0 then, in case.
Which ones are ones you're asking?
So the first one is 1 and the last row is 1, right? If we make these two also 0, is it still become a diagonal?
It is still a diagonal matrix. So the 0 matrix is also a diagonal matrix.
Sir, in a diagonal matrix, if any upper triangle and lower triangle is 0, then we call it as diagonal matrix, right? I mean, any square matrix that contain upper triangular matrix and lower triangular matrix having 0 elements, then we call it as diagonal matrix.
So
Is my definition correct?
no, so diagonal matrix, you don't need to go to upper and lower triangular. So it's enough if you just talk about the off diagonal entries, right? So off diagonal entry should be 0. Everything that is not on the main diagonal is 0 for sure. That is the only requirement for something to be diagonal. Whether the diagonal entries are themselves 0 or not is not a part of the definition. They could be 0, they need not be 0 also. Okay, so that's
Okay.
that's just a definition. Okay. So scalar, I hope you know, scalar matrices are some constant times the identity. So ideally, once we define this, we should define this and then define this because it's easier. So these are scalar matrices. Square matrices, you already know what square matrices are. Upper triangular matrix is one where everything below the main diagonal is 0. Okay, so meaning once again, right? So you don't say anything about these fellows. They could be 0, they could be non-zero. That is not something that is under your control. All that you need is that all entries below the main diagonal should be 0. Okay. Likewise for lower triangular, all entries above the main diagonal should be 0. Okay. So these are some special matrices you need to know. Transpose, right? Transpose is swapping rows and columns. So M cross N, A transpose N cross M. So Aij becomes Aji, right? All that,
Yes.
you know. So some properties, if you take transpose, once again, you get back the original matrix. AB transpose is B transpose A transpose. So all these are common properties. You will see a lot of symmetric matrices in this course, especially in weeks 5 and 6. So it helps to...
Sir, once could you go to the previous page once?
Yeah.
Okay, okay, got it. Yeah, you can go move out.
Okay, right. So A transpose equal to A. So that's a symmetric matrix. So how do you quickly see if the matrix is symmetric? You just tally off these things, right? So these are the symmetric entries. So they should be the same. So A transpose equal to A. What is skew symmetric? Have you seen skew symmetric before?
Yes,
Yes,
A
sir.
transpose plus equals to 0.
Yeah, A transpose equal to
Minus A.
Minus.
A, right? So what
minus and diagonal elements sum should be equal to 0.
Yeah. So is that a part of the definition, or is that a result of something being skew symmetric? So did you get the question? So if A transpose equal to minus A, is that sufficient, or should I also mention that diagonal entry should be 0?
Sir, I don't remember, sir. There is one condition if that is passing some. I couldn't recall. The same question even instructor asked me while he was talking about that point.
Okay. So let's start with A transpose equal to minus A, right? So A transpose equal to minus A. Let's look at the diagonal entry. So AII is a diagonal entry, right? So what is the transpose? When you transpose, do the diagonal entries change?
No.
No, sir.
No, right? So if you have A transpose and you look at the ith diagonal entry, that is going to be the same as the diagonal entry of A, correct?
Yes, sir.
And you know that
Yes.
A ij is minus A ji, right? So this is also minus A ii because it's skew symmetric. And with this, you are able to conclude that A ii has to be the only way it can be AIA can be equal to minus AIA is if AIA is 0,
Yes, sir.
right? So for a skew symmetric matrix, it's sufficient to mention that A transpose is minus A. The diagonal elements being 0 comes for free. Okay.
Yes, sir.
Okay. So there is a nice property involving symmetric and skew symmetric matrices. So any square matrix A, you can write it as a sum of a square symmetric matrix and a skew symmetric matrix. Okay. So this is actually not too hard to see. So if you go to this tab, right? So A is some square matrix. That's all you need. So and if you look at A plus A transpose, right? So A plus A transpose. What is the transpose of this?
A transpose
A
plus
transpose plus A.
Yeah, A transpose plus A, which is the same as A plus A transpose, right? Because matrix addition is commutative, so you can order
2A,
the
sir.
Yeah.
right. So this is symmetric. So A plus A transpose itself is symmetric. So this is symmetric. And if you look at A minus A transpose, and take the whole transpose, you will get
A transpose
A
minus
transpose.
A transpose
A
minus A, which
transpose
is
minus
negative of
A minus A transpose.
A minus A transpose, right? So this is skew symmetric. So therefore, if you add A plus A transpose, which is a symmetric matrix, and A minus A transpose, which is a skew symmetric matrix, you will end up with 2A, right? So you will end up with 2A. If you just rewrite this, you'll get A as half A plus A. This is also symmetric. So you're just scaling the matrix. That doesn't change the symmetry or skew symmetry property of the matrix. Okay. So this is what we have there. So any matrix, any square matrix can be represented as the sum of a symmetric matrix and a skew symmetric matrix. Okay, this is just some observation, not of great consequence, but it's good to know. Okay, so that brings us to the inverse.
Sorry, sir. Just in the previous slide, the skew symmetric has diagonals always 0.
Yeah, diagonals are always 0 by consequence of it being skew symmetric.
Okay.
Okay, it can't help being 0, the diagonals. So for a skew symmetric matrix.
Okay.
Okay, so that brings us to the inverse. Inverse is only defined for square matrices. Okay, so this all square matrices need not be invertible. So you have to be careful. So a square matrix is invertible if you can find another matrix B such that AB is equal to BA equal to I. So you know this. And B is called the inverse of A or A inverse. So for a 2 cross 2 matrix, it's worth remembering the inverse actually. Okay? So there's a simple way of remembering this. So if you have A, B, C, D, you just swap the yeah. So can you all mute? So I'm hearing some noise. Yes, you are not on mute. Yeah, thanks. So you swap the diagonal entries and you attach a minus sign to the off diagonal entries. Okay, this is only for 2 cross 2. So it's a useful tool to remember. Sorry, useful way to remember the inverse. Okay, and of course the determinant comes in the denominator. Okay, so some properties I'll just quickly go over them. The inverse of inverse is the matrix itself, and if you scale the matrix and take the inverse, you have to remember to divide by C. Okay, and just like transpose, if you take the inverse, the order of multiplication changes, and transpose and inverse are interchangeable operations. Okay, that is inverse, nothing more there. Determinants will once again be very useful in week 5. Okay, week 5 when we study eigenvalues and eigenvectors, determinants will play a very important role in computing these quantities. So please revise them. So you have this. What is this M called? Do you know? Do you remember what is M11, M12?
Minor.
These are the minors, right?
Yes, sir.
So these are the minors. So this is M11. You have M12. So this is your usual. You expand the determinant along any one of the rows or columns, right? So this is what you get. We usually expand along row 1, but remember
It's
that
5 o'clock.
remember that you can expand along any row or any column. Okay, so this expression is expanding it along the rows. Okay, this is expanding it along row I. So J is the column index. So 1 to n. So you can expand it along row I. You can also expand it along column J. Okay, so you will get the same value. Okay, you might have to do this sometimes, but usually just expanding along first row will be enough. Okay, so what is the cofactor matrix? This also you must remember. So Cij, so it's a n cross n matrix again. It's defined by -1 power I plus j mij. So these are all, this is just algebra here, matrix algebra. There's nothing deep about this. So adjugate is the transpose of the cofactor matrix, and you have a useful identity that goes by A into adjugate of A into A is equal to determinant of A into I. Okay, so and there is a link between determinants and inverses. What is that link? Do you recollect that?
If determinant inverse, the matrix is, we can find the inverse of the matrix only if the determinant is not 0.
Correct. Okay. So A is invertible if and only if, right? So this if and only if you must get used to if you are not familiar. So it is two-way implication, right? So A is invertible, then determinant of A is not 0. If determinant of A is not 0, then you can assuredly say that A is invertible.
Sir,
Okay.
once could you repeat this point? What is the meaning of invertible, sir? I don't remember.
Invertible we just saw, right? Inverse A into.
Okay.
This is the idea of inverse, right? So what matrix should you multiply so that you get the identity?
Okay.
Okay. So determinants and inverses, yeah. So A inverse, if you actually think about it, this is one way of, in school, those who have done math in 12th standard, 11th, 12th, you would remember
Yes.
that this is one of the ways of obtaining the inverse. Okay, in school we would have taught this, they would have taught us this laborious way of
It's
finding.
tedious.
Yeah, it's a very bad case. It's all algebra, but then such a boring computation. So you can rest assured that we will never ask you to do something as gory as this. Okay, so but you should know that this is actually a nice formula, because the determinant A comes in the denominator. It's immediately telling you that if the determinant of A is 0, then A inverse can't possibly exist, right? So it's not so direct, but it gives that nice impression to your mind that these two are connected. Okay, so one more thing.
Sir, what is algebra?
Yeah, you had a question, but there is some echo from your side. So if you can mute that and ask.
Sir, what is algebra?
Adjugate is just a kind of it's a type of matrix formed in a complex manner. Okay, so you have this you have these minors, right? The determinants that you compute, 2 x 2 determinants. So you put them in a matrix called the cofactor matrix, and you take the transpose of that matrix, you end up with something called the adjugate. It's not too important. Yeah, sometimes it's called the adjoint also, but adjoint we typically avoid that name because there is another adjoint in linear algebra. But so don't worry too much about this adjugate. Okay, it's just so it's a complex matrix. Okay, so you arrive by a complex process. So no need to worry too much about this.
Okay, sir. Okay.
Okay, so determinants and row operations. This is kind of important because it will help you compute determinants fast. So if you swap 2 rows, the sign of the determinant will change. If you scale a row by some value, say if you multiply a row by 2, the determinant will also be multiplied by 2. And if you add a constant times one row to another row, it will not change the determinant. Okay, this is very useful to compute determinants. So there are some consequences of this. So if a matrix has a row full of zeros, determinant is 0, right? And if 2 rows of a matrix, if they are the same, that's another instance of 0 determinant. So these are some things that you can keep in your mind, but the slide is not too important. You can move on, I think. This is important. So properties of determinant. So they are multiplicative in nature. So if you multiply 2 matrices, square matrices, you can compute the product. You can compute the determinant by computing the individual determinants and then multiplying them. Okay, that's very useful. This is also useful. Transpose doesn't change the determinant. Inverse just inverts the determinant. And this is something where you can get tricked. Okay, so if you multiply a matrix by C, the determinant gets multiplied by C power n. So why is this?
Sir, n is the order of the matrix, right? The
Yeah,
number of rows or columns. Okay.
It's scaling every row by the
correct,
C.
right? Yeah, so every row gets scaled by C. Therefore, by the property, by this property, right? Scaling a row scales the determinant, you will get C power n. So that's the reason. Okay, so that completes one. I have actually so many PDFs, but I have to cover 4 PDFs, but we have done only one. Maybe we can do it, do the rest. So I'll do one more and we'll see where that takes us.
Sir, you will share this PDF, right, with us?
Yeah. Even though, yeah, I'll share this. Yeah, I'll share this. Okay, so shall we, can we take a break for 2 minutes? We can restart it.
Yes, sir. Yes, sir.
Yeah. Okay, so shall we start?
Yes, sir.
Okay, so presentation, yeah. So, yeah, the next thing is extremely useful operation called or algorithm called Gaussian elimination, right? So, which is helpful in solving a system of equations. Now, this will be useful in weeks 3 and 4, particularly because we'll be looking at how to compute the row space, column space, null space, and all that, right? And how to solve a system of equations. So we'll be actually looking at Ax equal to b, and we'll also be looking at this concept called least square solution, where if Ax equal to b does not have a solution, what do you do? So you can still solve the system approximately, and there also least this elimination row operations are very useful. Okay, so yeah, this might be slightly new because some of you might have seen this before, some of you may not have seen this before. I'll be presenting a particular way of understanding row operations which are slightly different. Okay, so these row operations I hope you are all familiar with. So you can swap two rows. Okay, you can scale a row by a non-zero constant, and you can basically add two rows. In fact, you can simplify this operation as just adding two rows. You don't need to really look at it as add a constant times one row to the other row. So why is that? Why can I just replace? Can I just replace this with adding two rows? Would that still be the same?
No, sir.
Okay. Why will it be different? So I'll just ask. I'll repeat the question, right? So what I'm trying to say is, I have written three operations here. Okay. If I replace the third operation with adding two rows, right? Adding one row to another row, will that disturb the setup?
No, sir.
No, I think.
Okay, so it will not, because you can anyway scale a row by a constant and then you can add. Okay, so okay, so yeah, maybe it will. So there's a subtle change there, right? So you, in fact, it will. So maybe I'll take an example, and so what I was trying to explain is, what I was trying to get at is, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Consider this matrix. Now you have an operation. Let's say R2 is R2 plus 2R1. Okay. This is the operation that is defined in the third. So this is the third elementary row operation. So if I don't have that, if I only have add two rows, is that fine? Or is this operation entirely necessary?
It will be fine, I think.
Okay. So it is actually necessary, right? Because see, what are the first two operations telling you? You can swap rows. You can scale one row by some non-zero scalar. Okay. But then the third operation is telling you that you can not just add R2 and R1, you can add any constant of R1 to R2. Okay, so you need that specific third rule which says that add a constant times one row to another row. Okay, so I have made two things in bold here. One is that this is a non-zero constant. Okay, this is important. We'll come to why this is important in a minute. You'll understand why this has to be non-zero. You'll also understand why this has to be another row. So you can't add a constant to the same row. Can you tell me what will go wrong if you add a constant to the same row? Constant times one row to the same row. For example, can I do R2 equal to R2 minus or plus minus 1 into R2? What will end up happening?
No, we can't do two operations on one go, I think.
Zero.
Correct, yeah, that is wrong. But why is it wrong is what I'm trying to understand. So what will happen to the second row? Second row will become 0. Okay, so likewise, if you go back to this, if you scale a row by 0, that row will become 0. Okay, and this will cause problems. Okay, we don't want to make any row 0, a 0 row. Okay, so that's why these are in bold, and you have to always remember that this has to be another row and not the same row. Okay, these are elementary operations. Now we'll try to understand them differently. First operation is swapping two rows. Okay, so you are swapping row 1 and row 2. Okay, this is clear, right? What happens as a result?
Sir,
Yes, sir.
sir,
Yeah.
I have a small doubt. Sir,
Yeah.
like swapping two rows, does it give a negative sign outside?
Negative sign.
Outside the matrix or data?
Negative sign. Sorry, I didn't get it. Which negative sign?
Sir, no, sir, I have just a confusion. Like when we swap two rows, just after the process, do we have to give one negative sign also for swapping?
No, that is determinant, right? So if you swap two rows, then the determinant of the matrix will, the sign of the determinant will change. So that is different. Okay, so
Okay.
the determinant
That
of
was
this matrix will be -1 times the determinant of this matrix because you swap. Okay, not that is different from what you are doing here. Or you are only swapping the rows. You are not computing the determinant. Okay, so this is clear, right? So swapping rows is clear. Now there is an interesting way of viewing this. Okay, you can actually look at swapping the operation of swapping rows as multiplying by a matrix, pre-multiplying by a matrix. Okay, so I have written down the same matrices here. The one on the left is here, and the one after swapping is on the right here. I'm calling them A and R. Okay, how do I go from A to R? You can manually swap, or you could pre-multiply by a matrix. I'm calling that matrix E1. Okay, so this is where your vector matrix vector, that product will become very useful. So how can I view this? I can view this as row times matrix. That will be the first row here. So what is happening? You are like, this is like a very nice operation. This is 0 times the first row, 1 times the second row, and 0 times the third row. So what you are doing is you are selecting a row. So wherever there is a 1, you are selecting the row. So you are selecting the second row here. Therefore, this is 4, 5, 6. You are selecting 1 here. So therefore, this is 1, 2, 3. You are using 1 in the third place. Therefore, this is the third row of this matrix. Is this matrix product clear now? What has happened? Okay.
Yes.
So this is.
Sir, can you repeat once?
So what I'm trying to say is you have to treat this as vector matrix product here. That's how you have to look at it for easily understanding it. So the first row here is the product of the first row here and this entire matrix. Okay, so what is vector matrix product? A linear combination of the rows. So 0 into first row plus 1 into second row plus 0 into third row. That is the first row in the output. Likewise, the second row in the output is 1 into first row plus 0 into second row plus 0 into third row. So you can think of this as selecting the rows to be present in the final matrix. Is that clear?
Yes, sir.
Okay, so this is,
So,
yeah.
if I recall correctly, then if some row gets all the elements are 0, then it doesn't makes any sense to have that row, so our dimensions get disturbed. That's why we don't use two operations at once, right?
Two operations at once. So you can use two operations successively, but at once, yeah, it is a bit tricky. Right. So these are, it's better to do them one after the other and not at the same time. Okay, they have to, yeah, I hope that is clear. Okay, so this is,
my understanding is clear, correct, right, sir? regarding that, the row getting all the elements 0?
So when will all the elements be 0? That will come up in some of the operations, right? So if you have a rank deficient matrix, some of the rows might be 0. But I don't quite get what your question is actually. What you're saying is if you mix two operations together, some row could be 0. Is that what you're saying?
Yes, sir.
I don't understand how you could mix two, because you always do one after the other, right? At any point of time, you are doing only one operation. You're either swapping rows, or you're scaling rows, or you're adding constant times one row to the other. So can
Sir,
you?
in the previous slide, you said that we should not multiply by 2 row, add constant.
Yeah, row to itself. So you can't do R1 is R1 plus minus 1 times R1, right? So you should always do R1 is R1 plus something into R something else, right? So meaning you can add some other row to the current row. You can't add the row to itself. That is what I was saying, right? So
Okay, so
yeah,
we can't do one row with 2 rows. That was also
that you can
a
do, but yeah, that is not a problem as long as it is. For example, you can do R1 is R1 plus R2 plus R3, but let's not do that, right? So let's do it. Let's always follow these three. These are like atoms, right? So you respect atomic steps. Okay, so let's not mix or skip steps.
okay, sir.
Okay, so I hope this E1A is clear to everyone, right? What we have done, you have selected the rows.
So my question was only this, that if we miss those rules, then what can go wrong with our original matrix?
I'll come to that. It will become clear when I finish this set of slides.
Okay, sir.
Okay, so E1 into A is R. Now what we'll do is we'll try to go back. Okay, how do you go back? If you want to go from R to A, so if you want to go from R to A, what should you do? You should swap again. Is that correct? So yeah, you have to swap 1 and 2 again.
Yes, sir.
Okay, so how? So this is R, remember, and this is A. What should I pre-multiply with R so that I get A? What matrix should I pre-multiply?
The inverse
Inverse of?
of A.
So see, this is
of E1.
Good. Inverse of E1. What is inverse of E1? Can you see what inverse of E1 could be?
The same.
The same, right? It's actually E1 itself. So if you look at it, I'm calling it E2. So what is happening is the following, right? See, think about it as the same operation. What are you trying to do? You're swapping R1 and R2. So once again, you have to select the second column here and second row here and the first row here. Only then you'll get 1, 2, 3 here, 4, 5, 6 here. Okay. So what this shows is swapping two rows is a reversible operation. Meaning if you swap two rows to go from A to R, you can once again swap those two rows to go from R to A. And what governs this swapping is a matrix. We are going to call this an elementary matrix. Okay, so these are called elementary matrices because they help in the swapping process. Okay, so E1 helped us go from A to R. E2, in this case, E2 is the same as E1. You can verify that. So E1 into E2 is I. E1 inverse is E2, E2 inverse is E1. E1 equal to E2, by the way. So this is called an elementary matrix. So is this concept clear? That if you want to swap two rows, you have to pre-multiply by an elementary matrix. Is that clear?
Yes.
Yes.
Okay. So let's look at the next operation and you will see something similar happen. So you are scaling the rows. So you are scaling this by 2. Interestingly, you can achieve that using another elementary matrix where once again, the same idea applies, right? So this is 2 times the first row plus 0 times second row plus 0 times third row, and then the other rows remain the same. Therefore, it's just 1, 1. Okay. This is E1A is equal to R. So if you want to reverse this, if you want to go from R to A, this is R, A. What should be my E2?
Multiplied by 1 by 2.
Yeah, exactly, right? So this first element will be 1 by 2. So, okay, so it's half times the first row. That will give me back 1, 2, 3. Okay, and then rest are 0. So 1, 1 remains the same. So what do you think E1 into E2 will be?
I.
E1 into E2 will be I. Okay. So once again, what you have to remember is this is a reversible operation. So invertible means what? You can reverse things. Okay. So you can go from E1 to A to R. You can also go from R to A. Okay. Likewise, so this is another elementary matrix. Finally, you also have R1, say R2 is R2 minus 2 R1. So I have done R2 minus 2 times R1. Okay. What do you think E1 will be? There should be an E1 here also. So what do you think E1 will look like? Can maybe tell me that it should be a 3 cross 3 matrix. What will be the first row, second row, third row? If you have understood this so far, may I copy this and we can work it out here. You can tell me. So this is the operation. And I want you to tell me E1. So if I multiply E1 with A, so this is what A is becoming R. So, and I want E1 into A should be equal to R. So what should be E1? First, tell me what's the last row. Last row should be easy.
0, 0, 1.
0, 0, 1. Okay, you're retaining the last row as it is. Okay. What is the first row? That's also easy.
0 minus 2, 0.
First row. First row. Is the first row being selected here? It's being retained, right? So you're not changing the first row.
1, 0, 0.
Okay, 1, 0, 0, right? So what? This is the tricky part. So what should be this?
Minus 2.
Minus 2? And?
1.
1, 0, right? Exactly. So see what this is exactly what you're doing, right? So notice that you're retaining the first row, you are multiplying minus 2 times the first row and adding it to the second row. Therefore, this is 1, this is minus 2, and then third row doesn't make an appearance, right? So that is E1. Now, if
so
I have
if you retain the first one, sir, how is it 1, 0, 0? Why is it not 1, 2, 3?
Because you're retaining the first row, right? You're not changing the first row or the third row, so they have to remain the same.
So that's why it should be 1, 2, 3, right? Rather than 1, 0, 0. Why is it 1, 0, 0?
E1, right? We are looking at E1, not A. So E1 is right. So we are not looking at R, right? So R is the result of E1 into A.
Okay.
Okay. So E2 into R is A. So now we want to go the reverse direction. So that is E2. Okay. What do you think E2 will be? So you have to remember, you have to reverse this operation. You have to recover A.
1, 0, 0.
Okay. 1, 0, 0 again. Tell me the last row.
0, 0, 1.
Okay. What will be the middle row?
Multiplied by minus half.
Think again. So how do you reverse this? So you are subtracting 2 times the first row. So if you want to get back the original matrix, what should you do? Minus 2 R1. If you want to get back R2, the original R2.
Add.
Correct.
2,
Add 2 times the first row, right? So this is
2, 1, 0.
okay, right? So now what do you expect E1 into E2 to be?
I,
right? So let's quickly verify that. So this is, we can do our usual matrix multiplication. So this is 1, 0, 0. So this has to be 1. This is like 1, 0, 0, 0. Okay, so 1, 0, This will be 0. So this is minus 2 into 1 plus 1 into 2. So that is 0.
0.
Minus 2 into 0, 1 into 1. So that's 1. Minus 2, 0, 1, 0, 0. Okay. 0, 0, 0, 0. So this is 0. Correct?
Yes.
Okay, right. So that's what we will see in this slide. So this is, you go back. E1 is 100 minus 210 E2 will be 100 So remember that this is just the inverse. So R2 is plus 2R1 here, minus 2R1. And these are also reversible operations. So
Sir, sorry for interrupting, but I couldn't understand calculating E1. Is it necessary to understand how to calculate E1?
it is not necessary, but it gives you slightly more better understanding of the whole process. So maybe can you go back and watch?
Yes, sir. I will watch. My doubt was like, is it must and should for the upcoming weeks? Like,
No,
if
no,
I.
no, not necessary. As long as you
Okay,
know
okay.
how to do the row operations, that is enough.
Yes, sir. I know them. Okay, okay. No problem.
Okay, so now this will give you a sense of why you can't multiply by a. So now with this understanding, right? Why can't you multiply a row by 0? What will happen? What will break down?
It will be irreversible, I think.
Exactly, right? It will be an irreversible operation. So once you multiply a row by a 0, or once you add a row to itself with minus 1 as the coefficient,
Whole row becomes 0, 0, 0.
yeah, so you can't recover the operation. So this is very important when you want to solve equations. We'll see that soon. Okay, so we'll come back to this point, but now we move on to this row echelon form. Okay, REF, reduced row echelon form. So every matrix can be reduced to what is called its row echelon form. That there is this concept called leading entry or pivot. So the first non-zero entry in a row is called the pivot. So this is the condition for a matrix to be in row echelon form. So if you have 0 rows, they should all come at the bottom. The pivot or the leading entry has to be 1 always. And if you have pivot in a given row, it should always be to the right of the pivot in the previous row. So these are the 3 conditions. Some textbooks do not enforce that the pivot has to be 1. Okay, it's not a binding condition, but we will just assume that it's safer to have the pivot as 1. Okay, so yeah, these are some examples. So notice that this is the leading entry, first non-zero entry, first non-zero entry, first non-zero entry. These are all called the pivots. And the pivot in any row is always to the right of the pivot in the previous row. Okay, so that's what is happening here. So is this correct? Pivot is here, but the pivot is here. Is this correct? Does this follow the REF form?
No, sir.
Yes.
Yes or
Yes.
no? Okay, see.
Yes.
Yes, right. So see, this is coming to the right of this. That's all we care about. It may not be immediately to the right. That's not what the condition says, right? The pivot in a non-zero row is to the right of the pivot in the previous row. How far to the right is not mandated by the condition. Okay. All that we care about is it should come to the right. Okay. So therefore, these are all in REF. These are not in REF for different reasons. Why is this not in REF? What condition is it violating?
The pivot is not towards the right.
Correct, right? So the pivot here is to the left of the pivot in the previous row. That's wrong. What about this one?
It's again not to the right. It's below
All
it.
0 rows are not
Yeah.
in the bottom.
Exactly, right? Same. It should not even be in the bottom. It has to be exactly to the right. And what about this? Which condition does this violate?
All zeros should be at the end.
Yeah, all zero.
Sir,
Yeah, correct.
Sir, every column should have only one pivot element, right?
Yeah, every column. So some columns may not have pivots like this, but if a column has a pivot, it will be only one pivot.
Yeah, it should be one. It should be
Yeah.
one. Yeah.
So why is this not in REF?
Because pivot entry is not 1.
Yeah, because pivot entries are not 1. So this alone, you might see some textbooks calling this also REF, which is fine. Okay, so Even in max 2, this was fine. So max 2, if you remember, we didn't have this condition of pivot being 1. So don't worry too much. We won't ask you, is this matrix in REF in exam? So what is important is you must be able to compute the REF. Okay. So what is RREF? So when is a matrix in reduced row echelon form? What do you, if you recall, can you recall the conditions?
When it's in row echelon form and all the entries are either zeros or ones.
Okay.
Those
But all
entries.
Last row.
So it is an REF, that is correct. But
The
should all
upper elements are
go on?
the upper elements of the pivot rows should be 0.
Per elements, meaning you're saying the elements above the pivot are also 0. Is that correct?
Yeah.
Okay. What about below the pivot?
That also should be.
Okay. Right. Okay. So yeah. So first, it's in REF, meaning you have the matrix in row echelon form. So we have what is called a pivot column, right? So a column that contains the pivot is going to be called the pivot column. So for example, this is the pivot column, right? So sorry, what we have? Yeah. So these are all the pivot columns. This is a pivot column. This is a pivot column. This is a pivot column. So notice that the moment a matrix is in REF, all entries below the pivot will already be 0. That is granted, okay? Because of this rule. What is the rule? The second rule that you saw before, right? This rule will ensure that all entries below the pivot are anyway 0. Now, in the reduced row echelon form, all the entries above the pivot in the pivot column will also be 0. Okay, you can rephrase this as, in every pivot column, the pivot is the only non-zero entry. So this is the only thing that can be non-zero in this column. Okay. So mind you, this is still fine. Okay, this is not a pivot column. Therefore, you can have 2s and 3s or anything non-zero here. That's fine. Okay.
Yes.
Okay. Now let's look at some non-examples. So I hope this is clear, right? So this is in REF. Is this in REF, by the way?
Yes, sir.
Yes.
Yeah. Right. Only issue is that this is not 0. Okay. This also is in REF. Again, this is non-zero, so that's a problem. And what about this? Same, right?
Yes.
So
Yes.
if this were to become RREF, what would it look like? The final matrix. First row alone.
In first row,
1 0 0 2.
1002.
Yeah, 1002.
100
2.
2 or
Should be.
It can be 2.
Okay. No. So see, 10. If I want to convert this, okay. So if I want to convert this matrix into RREF, what should I do?
First row minus second row.
First row minus second row. It will become 100
1. Oh, minus 1. Sorry.
minus. Okay. All right.
Sir,
Okay. Yeah.
then in the left side, the first matrix is also not in like RREF, right?
See, you are only bothered about the pivot column, right? You are not bothered about what happens to other columns. See, here it could be -1 1 because this is not a pivot. Okay, what happens above the non-pivot entries is like not your concern. You are only bothered about what is there above the pivot columns.
Okay, sir.
Okay.
So we can swap the columns over here, right?
No, you can't swap the columns, right? So
oh, sorry. Yeah.
right. So these are all row operations. That's why these are called elementary row operations, right? You can't do anything with the columns.
Yes, I got it.
Okay. So the REF is not unique, but the RREF is unique. So that's a useful thing to remember. You can have only one reduced row echelon form for a matrix, but you could have multiple row echelon forms, right? So, okay. Now, this example, I'll just quickly walk through this. You can later on verify this. You might have done several of these before. So, what would you do here? Maybe I can ask that alone. So, what would be the first thing that you would do?
R2 will be R2 minus 3 R1.
Right. R2 minus 3R1. Okay. What next? What next? What
R3 will be R3 minus 4R1.
Okay, R3 minus 4R1. Okay, that's done. The first column is done. What will you do next?
We can just
R3
subtract R3
minus R2.
minus R2.
Okay, R3 minus R2.
And then R2
R2
divided by
5.
minus 5.
Okay. Are you done, or do you have something more to do?
R1 minus
So
2
if the
times.
goal is to find the
For
REF,
REF,
are you done?
it is done.
No.
For REF, it is done.
REF is done. Okay. If you want to go one more step and do the find the RREF, what will you do?
R1 minus 2 times R2.
R1 minus 2 R2.
R1 minus 2 R2.
Correct. Okay. So very good. So as long as you know this, it's life will be smooth sailing. So REF, RREF, this is how you have to compute.
Sir,
Okay.
so the difference between RREF and REF are like in a RREF, all pivot points the above and below would be 0, and REF need not be 0.
Yeah, above it need not be 0. Below it has to be 0 anyway. Above it need not.
Yes, sir.
Okay. Yeah. So why is this such a useful thing to do? So you have you did how many row operations? You did 1, 2, 3, 4, 5. Okay. So in general, you might have to do m such operations. Okay. And if you remember, each operation corresponds to pre-multiplying by a matrix. So this is what we call E1, right? So if you do m operations, you'll have m matrices, and you are applying them on the left, right? So you are first multiplying by E1, that will give you R1. If you multiply that by E2, that will give you R2, so on, right? So you're multiplying by a sequence of matrices. Each of them is invertible. We saw that, right? They're all reversible. Therefore, they're all invertible. The product of invertible matrices is also an invertible matrix. I hope you know that. Okay.
Yes.
Therefore, E is also invertible. So the nice result that we have is, if you want to convert a matrix into its reduced row echelon form, you can think about it as pre-multiplying by an invertible matrix. Okay. So converting from A to RREF is nothing but pre-multiplication by an invertible matrix. So that invertible matrix is what? A product of elementary matrices. So that's what we have come to. Pre-multiplication or left multiplication, whichever way you want to call it. Okay, is this idea clear? This is a very useful idea actually. Okay, everyone, can we move on?
Yes.
Okay, right. So where does this leave us? So this leaves us with the relationship between this and invertibility, right? So how do you make use of this to understand the inverse? What is this slide telling us? It's telling us the following, right? So if you have a square matrix, so first of all, can you do this row echelon form elimination and all that? Is this applicable only for square matrices, or can you do it for rectangular matrices also?
I think we can do for rectangular also.
Rectangular also.
Yeah, also, right? So it's applicable for any matrix. It's just that here we are only talking about square matrices. Okay, so you can do it for both. So these are two very interesting, useful results. So how do you know, or how do you find out if someone asks you, given a matrix A, is it invertible or not? First of all, how do you determine that it's
We
invertible?
find a determinant. If it's not equal to 0, then it's invertible.
That is one method. But if you were to make use of REF and RREF, whatever you see here is one method, right? So you find out the REF, okay? And if you look at the pivots, right? If you have a pivot in every column, A is invertible, okay? And if you look, in fact, if you go further, if you find out the RREF, what you will see is the RREF of an invertible matrix is always the identity matrix. Okay, is this clear to everyone?
Yes.
Okay, so the RREF of an invertible matrix is the identity matrix. So you can actually make use of this to find the inverse. So we can maybe do that some other day. For now, we can move on. Come to system of equations. think this is what we'll have time for. So this is system of linear equations. You have this form Ax equal to b. So you plug in all the coefficients into a matrix A, the unknowns into a vector x, and the right hand side into a vector b. So what you end up with Ax equal to is Ax equal to b. So if b is equal to 0, it's called a homogeneous system. Okay. So this is known. All this is known. Now we come to Gaussian elimination. Okay. So whatever we have been doing so far, this whole row reduction and elementary matrices and all that. Okay, I'll maybe come here. So what is the process? How do you solve this equation? So solve this system. What is the first step?
REF.
Even before REF, what do you do to this matrix and this vector?
Write it in a Ax equal to b form.
Correct, that you have done. But after that, what would you do? So
Concatenate it into one.
We include
Augmenting.
Correct.
Augmented.
Yeah. So you'll find the augmented matrix, right? You'll add concatenate as one of you pointed out correctly. So you put the phi 2 minus 1 on the right, and you think of that as an augmented matrix. So augment means addition, right? So and then you do row reduction, right? Is that correct?
Yes.
Okay. So you do row reduction only for this part, or do you do that for the
both of the parts?
Entire part.
Entire thing, right? So you do it for the augmented. That's why you augment in the first place, right? So you do row reduction on the entire thing. So let's move to this part. So you are trying to solve. You're trying to solve Ax equal to b, and in the process, what do? You augment the matrix. You call this A comma b, and you do row reduction. So row reduction will give you, let's say, the RREF. Okay, I'll call that R, and then it will give you something. Let's say it's called C. Okay. So you have reduced. What have you done? You have reduced the system Ax equal to b to the system Rx equal to C with the help of elementary row operations. Okay, this is what you have done. Now, what you claim is, so what do you do now? So you solve Rx equal to C. Okay, that's what you do. But then, how do you know that solving this will give you the solutions to this? Are these not two different systems?
Sir, can you show the augmented bit with the example, like over here?
Okay, so we'll take this matrix itself. So what you have is A is 2 minus 3, 4, 1, 1 minus 1, and 3 minus 1, 5, right? And B is 5, 2, 1. Okay, so the augmented matrix usually represented as A slash B will be, this fellow goes in here. Convenience of using a computer is you can do this copy paste business. Okay, and this 5, 2, 1 will go here. So this is the augmented matrix. Okay, now what I'm claiming is once you do row elimination, row reduction, you get RC. Okay, in this case, I don't know exactly what R and C will be, but you will get some R and some C here. Okay, so and you will solve Rx equal to C. What right do you have to claim that the solutions to this system will also be the solutions to this system? Yeah, one.
Whatever we are doing on the left hand side, we are doing same on the right hand side, so the system won't change, I think. So if the previous has a solution, then the second one also has a solution.
Okay. In terms of what we have studied so far, can you refine your answer? It's correct, but what is each row operation? It's actually
reversible.
is reversible. So each row operation is what? So remember, every row operation, you start with Ax equal to B. Every time you do a row operation, you are pre-multiplying by some matrix, okay, which is invertible. So you should do it on both sides, okay. Then what you do, maybe that's your first row operation. Then you do one more, right? So you do that on both sides. And then you keep doing it m times, right? So there are maybe m row operations. So here also you should do the same thing. Okay. And each one of these is reversible, meaning if you want to go from, so this is what I call Rx equal to C, right? So this is Rx equal to C. So this whole thing will be R. Okay. This whole thing would have become R and this whole thing would have become C. Okay. So what gives me the right to connect these two is that I can, if I invert each of these operations, okay, if I do EM inverse, EM minus 1 inverse, so on till E1 inverse, I can go back to AX equal to B. Okay, that is why Gaussian elimination works. Okay, this is an important point. You should understand that AX equal to B and Rx equal to C are effectively one and the same system, right? So if you solve one, you solve the other.
Yes.
Is this point clear to everyone? What has happened? At least vaguely, if not entirely.
Yes, sir.
Okay, so that's what is happening here. So this is what I have written down here. You start with Ax equal to B and then you do sequence of row operations that is reversible in nature. Therefore, you go here and these up down arrows are telling you that you can at any point of time go from one to the other. Okay. So this is called forward elimination. Sometimes it's called forward elimination because you're moving forward top to bottom and eliminating a lot of entries in the matrix. Okay, you get the augmented matrix and you do ABRC. This is what we just did now. Okay, and then you get Rx equal to C. You solve that. So you have some terminology. What is this terminology? You have n variables. Okay, some of these are going to be called pivot variables or dependent variables, and some of these are going to be called non-pivot variables or free variables or independent variables. Okay, in this terminology you must get used to. There's an example coming up, so it will become clear. How do you solve? Will also become clear. Maybe I don't want to explain this now because it's better with an example. So let's take this example. Assume that you had Ax equal to B, and then you did Gaussian elimination, and you have a matrix in RREF form. Okay, this is after you have done row reduction. So I'm assuming that you can do that on your own. So that is the simple part. Now we have to solve this. Okay, forward elimination is done. Now we have to solve this. So how do you solve this? Do you remember how to solve this system?
Yes, sir. Like we will take each column as X, Y, Z and equate it. Like for example, X minus Y is equal to W. Sorry, 1.
X minus Y plus W plus W
plus W times 0. Right? Sorry,
No.
Z times 0.
X minus Y minus W equal to 1.
Minus W is equal to 1, but that's correct. But how do you? That's like rewriting it as
W is I think
matrix
free
multiplication.
variable and Z the free variable, so we'll assign T or something to it and represent it the
correct. Yeah, that's the way we do it.
Backward substitution.
Yeah, so this is called backward substitution. So you have done forward elimination. Now you have to go backward. Now this is an important step. So I want you to get this. So because the Gaussian, the elimination part is easy, right? The forward elimination is easy. Going back is important. So what are the pivot columns?
Second and fourth.
Pivot columns.
Yeah,
first and third, sir.
First and third, right? So this is a pivot column.
The bold ones. Yeah.
Okay, these are the pivot columns. Now, the variables corresponding to the pivot columns, what are they?
X and Z.
X and Z. Okay, so they are going to be called you can either call them the pivot variables. That's what Professor Prashant will use. I think that's the term he will use in week 3. So x and z are called the pivot variables, or you can also call them dependent variables. Okay, so they are kind of dependent on the pivots, kind of fix them in place. So they are dependent on what comes to the right. Okay, w and y are what remain. They are called the
independent of free variables.
Independent or free variables, exactly. Okay, so please keep this terminology in mind. Do not get confused when you watch the lectures. So one prof uses free variables, the previous prof would have used independent variables. So they are the same thing. Okay, so now what do you do? So y and w are independent, x and z are dependent or pivot variables. Okay, now what you do is, since these are independent, y and w, you can give them any value. Okay, you can give them 1 0 minus 1 2, whatever it is. So in general, you can give them some arbitrary values t1 and t2. Once you fix them, what is dependent on them? X and z are dependent on y and w. You can compute them using these equations. So can you tell me what z will be based on this? So this is the equation where z appears. Z depends on which other variable?
W.
W. So what's the value?
Minus 2t.
Minus 1.
Minus 1 minus 2 W.
Minus 1 minus 2 W, but W is T2, right? So it is minus 1 minus 2 T2, right? What about X? X is the next dependent variable. X depends on Y, Z and W. Z, of course,
can be written as T2. Sorry, in terms of W, right? Z could be written as in terms.
Yeah. So now can you tell me what X will be in terms of
1
T1
plus T1 plus T2.
1 plus T1 plus T2. Okay, so let's see. So 1 plus T1 plus T2 minus 1 minus 2 T2. Okay, is this clear to everyone? What we have done?
No,
okay.
sir.
Sir, you're transferring it to the right side of the equal to, right?
Yeah, I'm just solving this.
Okay, got it.
Yeah.
Sir, one more time, please, sir.
Yeah, so you just have to expand this equation. So if you expand this, what will you get? Z plus W equal to minus 1. Correct? Sorry, Z plus 2W equal to minus 1. So Z is minus 1 minus 2W and W is T2. That's all I'm doing.
Can you write and show, sir?
Yeah, write, sir. If you can write, because it is confusing. I'm not able to get it.
Okay. So what are we doing here? This time I will write, but next time you should write. Okay. In the exam, you should get used to doing these things. Okay. So what is this equation? Okay. What is the last equation? 0 into x plus
0y plus 0 z.
Okay. 0. Correct, right? This is okay, no?
Yes, sir.
What is the second equation?
0x
0x plus 0y
0y
plus z
1z
plus 2w
plus 1z plus
2w
equal to
2w
minus 1.
Okay, what is the first one? 1x minus
minus 1y.
Okay, this 1x is very awkward. I'll just say x minus y
X minus y
plus minus
w
minus w
equals to 1.
Okay, so this is clear, right? These three equations, I'm just converting from matrix to equation form. That's all.
This is clear, sir. Now,
yes, sir.
Yeah, now what do? You have to solve for this first equation is useless, so let's get rid of that. Yeah, so now what you have to do? You have to solve for so sorry, in the process I messed up the equation ordering. Okay, this should come first. Okay, this is the first equation, this is the second equation. Okay, so now what you have to do is you have to solve for z. So z is what? Minus 1 minus 2w. Okay, And what we have called W as, so we have called W as T1. What is the other independent variable?
T2.
Y, right? So you can use T1 and T2 interchangeably. So it isn't better. So this is -1 minus
Two times T1.
T1, right? So that is, so you have now found out Z. See, the goal is to find out everything in terms of T1 and T2. So you already have, so you need to find X, Y, Z, W in terms of T1 and T2. That's the goal, right? So, and you assume in this process, this is T1, this is T2, and you have solved for this, which is -2T1 minus 1 minus 1 minus 2T1. And then X is what remains, right? So this is what X is equal to 1 plus Y plus W. So 1 plus, what is Y? T2, right?
Yes.
T1. Yeah, so that is what we have there. So this is 1 plus T1, T2, 1 minus 1 minus 2 T2, or T1, right? Depending on what you have to press, T1 and T2. Okay.
Now clear, sir.
Okay, now if you put the solution together, this is the solution to the system. Okay, so this is like one solution to the system.
It's 6 o'clock.
And if you allow T1 and T2 to vary, you will get all possible solutions to the system. Okay, so this is the set of all solutions to Ax equal to B here. All right, so this is fine, right?
Yes, sir.
Okay, so we have few more slides here. So in general, if you have Ax equal to B, A is M cross N augmented matrix, you convert that to RC. So this is important to know. So the number of pivots is the number of dependent variables. So what does that mean? So you have two pivots here. Therefore, you have two dependent variables, X and Z. Okay, so therefore the number of pivots is equal to the number of dependent variables. So what will be the number of independent variables? Therefore,
Non-infinite.
how do you express that? In terms of M and N, what can you say about the number of dependent variables and number of independent variables? If you add them, what should you get?
N.
Number of columns.
Right? N, or number of columns, right? So number of columns or N. Okay, please note this. This is actually, so now we come to the final part, which is Ax equal to B is there, but there are three possibilities. There is either a solution or there is no solution, right? Two general possibilities. Within there is a solution. What are the subparts?
Unique or infinite?
Sir, infinite solution and unique solution.
Right? Can we have two solutions alone?
No, sir.
No, right? So that's not possible. It's either unique or infinite. So the no solution, right? You can actually find out from the row echelon, this RC itself. So if it has a pivot in the last column, it has no solution. So I just go back to this very quickly. Assume that you have a this is RC. I'm telling you showing you the augmented matrix after row reduction. Let's say it looks something like this. So 1 0, so 0 0 1 minus 1 0 0 0. Okay. This could be something else. Doesn't matter. So is this matrix? It's a 3 cross 3 matrix. Is this in RREF?
Yes.
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 Okay, so this is the B part, and B has become C. So Ax equal to B has now become Rx equal to C. So this is R, and this is C. Does this have a solution?
No, sir.
Non-zero values.
Yeah, so you have, so this last equation, if you look at it, it's of the form 0x plus 0y plus 0z equal to 1. Therefore, this does not have a solution. So this is what I meant when I said that there is a pivot in the last column. So last column meaning the column corresponding to B. Okay. So if you have a pivot corresponding to the last column, meaning the C column, then Ax equal to B does not have a solution. Okay, is this clear?
Yes, sir.
Okay, so now we come to the solution part. So if it has a solution, when do you think it has a unique solution? What should be the condition using this information here?
If we have only
when
pivot
there are no
elements.
independent variables.
Exactly, right? If you have no independent variables, if everything is dependent, then there is a unique solution. Okay, because you have no control over what you can choose, right? If you go back, there are infinite solutions here because you had liberty to choose T1 and T2 to be whatever you want. Okay, so the moment you have independent variables, you have infinitely many solutions. The moment you have no independent variables, if everything is dependent,
You have a unique solution.
okay, so unique solution. Okay, if all are dependent, unique solution, there is at least one independent variable, infinitely many solutions. Okay, so in general, there is a does that come? There is a nice thing that comes in the next. Okay, that comes in the next set of slides. Yeah, so this is the end of the slide deck. Okay, that ends Gaussian elimination. So any questions so far in this?
No, sir.
No, sir. Sir, for no solution, the last column of pivot should be 0, right? Like if all are 0, 0, 0, and
Yeah,
1 is there,
correct.
for
Yeah, the
example.
last column of the augmented matrix has to have a pivot in the final.
Yes, yes.
Yeah.
Okay, got it.
Sir,
Okay.
is there a list or something that tells us what are the conditions for having unique solution, no solution, and uh, infinitely many solutions? Because we see this in determinant, we see this in Gaussian elimination. There are many ways that we can find out. I mean, can there be a composite list or something that can tell us that these are the cases where we will have a solution, no solution, and unique solution or something like that?
You could compile one such list. You mean to say different approaches, right? So
yeah,
we
helpful in the exam, right?
Yeah, you could compile one such list that maybe we can do. See, there is one. So there is one nice uh, chart like this that will come up when we study this null space, row space business. So there is you can form a graph like this. Okay, but for that we have to look at column space, null space. That's another way of understanding, but maybe we can't do that today. Today we
Okay,
have done the 2 hours. So I also wanted to do vector spaces because the next week 3 starts with. The problem is there are too many things to cover today. Okay, so we can't cover this today. Let's see.
Sir, we'll cover this in the next session, sir. Next 2 sessions without the solve with us for week 3.
Yeah, we can do that. Yeah,
we can do that, sir.
So this was week 2 or week 3?
This is preparation for week 3 actually.
Okay.
Okay. Yeah. So anything else? If not, we can.
Thank you so much, sir.
Yeah.
Sir, it is very this thing that I may forget, sir. So any I asked this question last time also, sir. The study material is not there, na, sir. If you can compile something like that, that will be helpful, at least with the syllabus part.
Yeah, see, I am working on a set. So I had a set of notes for ML for the linear algebra part. There are actually other notes also. Do you all know Anand Kumar's notes from?
Sir, if you can share it with us, it will be very helpful, sir. Maybe on the discourse or wherever.
Yeah, so Anand Kumar was the TA for MLF. He has done a great job in writing set of notes. I'll share my notes whenever they are ready. So see, these are my notes in the progress. They are still in the progress stage. So
where can we get Anand sir's note? I mean,
I'll just share that. Yeah, so we just have to find out the.
So if you can put it in discourse, it will be helpful.
Yeah,
sir.
he has already put it in discourse. So this is Anand's notes. So it's already there on discourse. So you have to just.
Okay, sir.
That is very useful. He has done a very good job. He has done a great job actually. So he also starts from week 3 because week 1 and 2 are not too hard. So he'll start from, it's like neat summary of all the concepts in that particular week. Do that. If you want something slightly more verbose. So I am working on something that's like, but that'll take you, that'll give you like slightly too much information. So it will give, for example, it will tell you what are vectors, what are matrices. It will tell you what are data sets, and so it will also tell you what is an ML problem. So it might be more detailed than what you like, but I'll share both of them.
Yes, sir, please.
Yeah. Okay. Yeah. So anything else? If not, we'll.
Thank you, sir.
So I have a doubt from other week. Uh, like, sir, what is norm function? Like,
Norm. You mean NORM?
yeah, sir, norm function.
Yeah. So the norm is a function that allows you to compute the length of a vector, right? So if you have a vector, let's say 1 comma 2, then norm of 1 comma 2 is usually taken to be square root of 1 square plus 2 square. Gives you the length of the, so norms and dot products, right? They can give you the geometric idea. So things like angles, distances. So norm is associated with the distance. So it gives you the distance of a vector from the origin. That's what it does. We will look at norms. Yeah, very soon we'll look at norms. Once we come across this dot product concept in more detail, we'll.
Okay, sir. Thank you, sir.
Yeah. Okay, then. So shall we stop then and meet again soon?
Yes, sir. Thank you.
Yeah. Thanks, everyone.
Thank you, sir.